Okay, so let's talk about context-free languages and context-free grammars which generate context-free languages. Okay. Now, let's take English as an example of, a language that has a grammar. So if I say, the cat drinks milk, you all look at me and say, yes, that's a valid sentence. Okay. Dog the hill the up ran, gibberish. Okay, so we all know how to decide whether or not an English sentence is valid or invalid. But it's also useful, and in a pinch, you could generate valid English sentences. For example, when you write an essay. Okay? So certainly it's useful to be able to generate the strings of a language, to generate valid strings. Okay? And it turns out that, even though formally speaking, the goal is you have a yes set which defines a computing problem, and given an input string, you'd like to say yes or no, does it belong to the string, to the set. The ability to generate the strings in a set, okay, and we'll be focusing on this set for the moment, the one that gave the DFA a lot of problems. Okay, the ability to generate the strings in a set can be used, okay, in order to solve the problem, in order to decide if an input string belongs to the set. So let me show you a quick example of that, and we're going to use, we're going to dig back deep into our vault and remember recursive definitions of sets. So here's a recursive definition of this set consisting of, strings of zeros followed by an equal number of ones. So we start with a base case. So recursive definition of L. Okay. So you have a base case epsilon, the empty string is in L. Okay, you have a constructor, and I'm just going to write it out. Okay, the constructor is if x is in L, then 0x1 is in L. Okay, and nothing else is in L. Okay, and so this is the base case, this is the constructor, and this is the minimality clause. Okay, which basically says that that this is the smallest set that satisfies my first two clauses. Okay, and what does this do? What this does is it allows me to generate strings. So I can start with epsilon. Okay, that's in my language. Now if x is epsilon, then I generate 0 epsilon 1, which is 0, 1, okay, and so on. And then I would generate 0, I can plug in x equals 0, 1, so I get 0, 0, 1, 1, 1, 0, 0, 1, 1, so 0, 0, 1, 1, okay, and so on. Okay. Now let's consider two strings, 0, 0, 0, 1, 1, 1, okay, and 0, 0, 0, 0, 1, 1. Okay, so the computing problem. Okay, and it's clear that this string is in L and this string is not in L. Now, how does being able to list the strings allow me to come to that same conclusion? So let's continue listing the strings. So the next guy that's listed is, I plug in x equals 0, 0, 1, 1. I put a 0 here, a 1 here. I get 0, 0, 0, 1, 1, 1. And I observe that I have generated this string. So therefore, this string is in the set defined by this recursive definition, and I'm claiming that that recursive definition is actually that set. Okay, so check, yes. Well, technically what we have shown is that this string is in this recursive set. Okay, and now let's keep going, let's keep generating. My next one is 0, 0, 0, 0, 1, 1, 1, 1, and we could keep going. But at this point we pause and say, this guy has length 6, this guy has length 8. Okay, and because I'm listing out the strings in a systematic order, in order of increasing length, I can now conclude that this string is not in my recursive set, which is actually that set. Okay, and how do I conclude that? Well, because all future strings are going to be longer than 8 bits, and this is a 6-bit string which hasn't matched anything that I've generated so far. So it doesn't match what I've generated so far, and it's going to be shorter than everything that comes. So therefore, it's not in my set. Okay, and this is just to show you that if we can generate the strings in a language in a systematic way, okay, then I can use that ability to list in order to actually solve the problem, in order to take an input string and decide whether or not it's in my set. Now, that might not be an efficient way to do it, okay, but it's a way to do it. And right at the moment, we're just talking about ways to solve computing problems. Okay, now, I'm going to give you the context-free grammar version of this entire process. Okay, so I'm going to give you a context-free grammar that generates this language. Okay, and context-free grammars, which are giving you the ability to list out generate the strings in a language are very useful anytime you need to, be able to take a string and in some sense be able to parse it and say, is it or is it not valid? Parse it is essentially asking the question, can I generate it using my grammar? Okay. And this is used all the time. Compilers, HTML parsers, arithmetic expression parsers, and so on and so forth. We represent all these things. We represent the valid computer programs by a grammar. Okay. And then you give me a program, you write a program and send it into your compiler. The compiler parses it and then says valid or not. Valid means yes, we can try to run it and see what happens, or not, some kind of syntax error, something is wrong. Okay. So grammars are very important. We will touch on them, okay, just to give you a flavor of what's going on. Okay. But you will see much more about this in, say, a programming languages course. Okay, so we're going to use this to illustrate context-free grammars, and let me just write down the context-free grammar for this same language that caused a problem for DFAs. Okay, and that will immediately show you that context-free grammars are already stronger, more powerful than DFA, because I can solve a problem that DFA couldn't solve. Okay. And then we will argue also that they're as strong as DFAs. They can do everything DFAs can do. So not only can they do everything that DFAs can do, but they're strictly stronger. Okay? That makes it very powerful because DFAs are powerful. Okay. So here's the context-free grammar. I'll write it down and then we'll talk about it, and then you'll basically know everything you need to know about the rules for context-free grammars. So the first rule for a grammar that, let's say generates this language. Okay, so let me say we're going to talk about a context-free grammar for 0 to the n, 1 to the n. Okay. And we will write it as CFG. Okay. Let's say 0 to the n, 1 to the n. So to indicate that we're talking about a context-free grammar for the language 0 to the n, 1 to the n. And I'll briefly touch on why we call this a context-free grammar. Okay. But first let me show you what the context-free grammar is. So it has rules, and in this case we're going to have two rules. Okay. And the first rule, so it has rules, it has variables, and rules for changing variables. Okay. And the most important variable is what we call the start variable. So we have a start variable, I'll call it big S. Variables are usually in big letters. Okay. And the start variable can transition to epsilon. So this is an example of what we call a production rule. So that's the first production rule. And there's another production rule. This start variable can transition to 0, start, 1. Okay. So these are called production rules. Okay. And in our case, we have two of them. Okay. Now, as I said, just like in the recursive definition, the context-free grammar is a way of representing a methodology for generating the strings in a language. Okay. And you can see the similarity with this recursive definition. You have the base case. This is sort of, you can think of this as a base case production rule. Well, we call the epsilon here a terminal, not a variable. So, if you generated epsilon, you were done. And we call 0 and 1 terminals. So S is the variable. And it turns out you can have more than one variable. And the terminals are epsilon, 0, and 1. These are terminals. Okay, and what that means will become clear when we discuss, the rules for how to generate strings. So the rules for how to generate strings. Okay. So step 1. And now I'm essentially defining for you, what a context-free grammar is. Okay, step 1. Write down the start variable. Write down the start variable. Okay. And how do you know what's the start variable? Okay, so in the production rules, on the left of a production rule are what we call the variables. Okay, so on the left are only variables, and on the right can appear terminals and variables. Okay. And the start variable is the variable on the left in the first rule. So we'll take that as, the default. Okay. Otherwise, I would have to specify what's the start variable. So, in this case, we would say S is the start variable. Or we can just by default say that you always put the start variable as the first rule. Okay. So write down the start variable. So let's do that. So we write down the start variable. Now, okay, what you have to do is you can take whatever your current working string is. So, step 2, take your current working string and replace a start variable. Okay, so that's the second step in the rules for generating strings using context-free grammars. Okay, and so how do you replace a start variable? So you find a rule with, so you replace a variable. So you find a rule with the variable on the left. So find a rule with that variable on the left and replace the variable with what the string on the right. Okay, so when I say rule, I mean find a production rule. Okay, and so let's see some examples. So we have our current working string s. So it has a variable s. Okay, so we would say, okay, I'm going to replace this variable s. So I look for rules which have s on the left. Okay, and I could replace s with whatever's on the right of such a rule. So I could replace s with epsilon, or if I chose this rule, I could replace s with 0 s1. Okay, so I could replace s with epsilon, okay, and this would be an application of rule 1, or I could replace s with 0 s1, and this would be an application of rule 2. Okay, and the final rule for using context-free grammars is you keep doing this until your working string has no more variables. So keep doing until working string has no more variables. Okay, so these are the rules for using a context-free grammar. Okay, so let's see. I took my start variable, I replaced with epsilon. Are there any more variables? No, so I'm done. Okay, so this is a string that was generated. If I had gone this way, I cannot be done yet because I still have variables in this string. Okay, so I look at this guy and I say, okay, I'm going to pick s and I'm going to replace it with, I'm going to use a rule to replace it with what's on the right of the rule. Okay, so I would replace it, I could replace it either with epsilon, so I could apply rule 1 and get 0, 1, 0 epsilon 1, which is 0, 1. Or I can apply rule 2, okay, and replace this s with 0 s1. So I have a 0. I replace this s, and I'll put it now in red. I'm going to replace this s with 0 s1, okay, and I have my original 1. Okay, and in this case, I would have generated 0, 1, and I'm done because there are no more variables. Okay, and in that case, I'm still not done because I have the variable s still in my string. Okay, and we can continue. Okay, so if I had gone this way, I'm not done, but I could apply rule 1 again. Okay, and I get 0, 0, epsilon 1, 1, because rule 1 says replace s with epsilon. So I get 0, 0, 1, 1, or okay, I get 0, 0. Okay, now I replace s if I'm applying rule 2. So if I'm applying rule 2, okay, I get 0, 0. Okay, that's this 0, 0. I replace s with 0, s1. So I'll put that now in blue, 0, s1. Okay. And then I still have my 1, 1. My 1, 1. And you get the picture. Okay, so in this situation, I'm still not done because I have a variable. Okay, and I could either replace it with epsilon or keep going. And if I keep going, I have to keep going, and so on and so forth. Okay, and every time I get to a string that has no more variables, that's a string that was generated. Okay. And so here you see I'm generating epsilon 0, 1, 0, 0, 1, 1. If I put epsilon here, I'd get 0, 0, 0, 1, 1, 1, and so on. Wow. I'm generating exactly these strings, just like the recursive definition. And that's the language L. And we say that this is a context-free grammar that generates this language L. Or we would just say this is a context-free grammar for this language L. Okie dokie. And now some conventions. Okay, so we will say, so for example, here, so let's take this path. So we will say S, with rule 2 goes to 0, S1, with rule 2 goes to 0, 0, S11, S11, okay, and then with rule 1, 1 goes to 0, 0, 1, 1. Okay, so we will say that this is a derivation of 0, 0, 1, 1 in the context-free grammar in CFG 0 to the n, 1 to the n. So in that context-free grammar. And sometimes we will write that, S, can lead to, or from S can be derived 0, 0, 1, 1. And we sometimes put a star up here to indicate, using a bunch of rules, we can go from S to 0, 0, 1, 1. That means that 0, 0, 1, 1 is in the language that's defined by S, in the language that can be generated by the context-free grammar, okay, that starts with the start string S. Okay. And one more convention. Okay. Typically we like to condense all the production rules that involve one variable into just one line. It's much easier. Okay. And so what we will typically do is we will say, okay, we just have one production rule, and we will say that S goes to either epsilon, and we will do an or symbol. So that's that vertical bar. S goes to epsilon or 0S1. So we combine those two production rules into one production rule. Okay. So just to be very explicit, this is actually two production rules, but we've just used a shorthand to represent the two production rules. There's this production rule and that production rule. Okay. And so, we could, if we wanted to tweak this second step for generating strings, saying, find the production rule with your variable on the left, okay, and then, replace that variable with one of the options on the right. Okay, so this is an or. Okay, so that's a very simple context-free grammar. Okay, to introduce you to context-free grammars. Now let's do lots of examples. But before we go to examples, let me just emphasize that effortlessly we have produced a context-free grammar that generates this language, which was too hard for the DFA to solve. Okay, so that just shows you the power of context-free grammars for generating languages. Okay, so let's erase, come back, do lots of examples. Okay, we might as well go for speed. Bam! Okay, so let's do a bunch of examples, and I highly recommend all the pop quizzes and exercises in the chapter, especially for those of you who are not familiar with this material, the theory of computing. This is all new stuff. So do the exercises and pop quizzes, especially pop quiz 25.1. Okay, but now, so quick summary of what a production rule is. Okay, just to remind you again. So a production rule takes a variable, okay, to an expression or a string. Okay. And the variables are typically P, Q, R, S, T, and so on, capital letters, and the expressions can contain any string that contains variables and terminals. So variables and terminals. Okay, and the variables are the same variables that could have appeared on the left. Okay. And the terminals are typically the empty string 0 and 1, but you can define whatever terminals you want. Okay. And sometimes we label the variables in other ways when it makes it easier to understand what the context-free grammar is doing. Okay. So now let's take an example and try to do all the derivations that I'm doing. Try to do them before me. Okay. That'll help you with learning. Okay. So let's take a context-free grammar, which is with one variable, the start variable, which can transition to either epsilon, 0s, 1s, or 1s, 0s. So the first thing I'll ask you is how many production rules? Give you a couple of seconds. 1, 2, 3, 4. Boom. If you're back, and you said 3, correct. So you can either, one production rule is S to epsilon, another production rule is S to this string, another production rule is S to this string. Okay. Now you will notice there's only one variable S, but when S transitions to this string, there are 2 appearances of S. That's perfectly valid. Okay. Next, give a derivation. Give a derivation of 0, 1, 1, 0. Okay, so go for it. Give a derivation of 0, 1, 1, 0. I'll give you a few seconds. 1, 2, 3, 4, 5. Okay, now I'm going to do it. So let's start by writing down the start variable S. Okay, and then this guy can transition. Okay, to I'm going to make him transition. This guy, I'm going to make this guy transition using this rule. So this you could. Okay, so technically this is rule 1. Okay, and I'm going to transition S by replacing S with 0s 1s. 0s 1s. Okay, perfectly valid. So I transition to a string with more than one s, no problem. Okay, now, in order to make my next step, so I can't be done yet because I have strings. I have variables s. Now, in order to make my next step, I can pick whichever variable I want. Okay, so there are 2 variables appearing. I can pick whichever variable I want, either this s or that s. Okay, so let me. Oh, sorry. We typically use a double arrow here. Okay, and so this guy can transition. So let me pick. I'm gonna pick, for example, this s. Okay, and so I'm gonna transition from. I'm going to replace this guy, so I need to pick now I've picked a variable, now I need to pick a production rule. So I'm going to replace this guy with epsilon. Okay, so this is still, there's only one production rule, so I'm going to replace this guy with epsilon. That becomes a 0 epsilon 1s. Okay, now I need to pick, now I have only one s, so I'm going to replace this s. Okay, with my rule 1. So I'm going to replace this s with this production rule. So s goes to that guy. So this is 0 epsilon 1 is 0, 1. Now I replace this s with 1s, 0s. 1s, 0s. Okay. So I hope you're following very carefully through every step. In fact, I hope even something better, that you already did all this. Okay. Now, if you're not getting exactly these same steps, that's fine. Okay. There can be more than one derivation of a string. Okay. And so from here, we see that we're almost done. We were going after 0, 1, 1, 0. We've got 0, 1, 1, 0, and we've got s's here, but I can replace the s's with epsilons. Okay, so I can go, with 1, 0, 1, 1, epsilon 0, which is 0s, and then I can replace that guy with 0 with epsilon, so I have 0, 1, 1, 0 epsilon, and then I'm done. Okay, so I've derived this guy. Long derivation, but that's fine. Okay. Now, one thing I want to point out about this derivation. Let's look at this expression. Okay, so let's look at this expression 0s 1s. Okay. Now, you might think that, it's s here and s here. Don't I have to replace them with the same thing because it's s in both in both spots? Okay. Now, I want to contrast that with the following mathematical expression that involves a mathematical variable. Okay. So, let's say 0x, 1x, where x is just standing for something that's unknown, but it's the same unknown thing here and here. So, if I set x equals to, let's say, 0, 1, then this would be equal to 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1. Okay. But you will notice that in this derivation, okay, this s became epsilon at the end of the day. So this s became this epsilon, and this s, okay, so we have a 0 epsilon, okay, and then there's one s. So this s, okay, so this s became at the end of the day 1, 0. Okay, became. Well, it started off by it stayed the same. Okay, so it stayed the same. Okay, then it became 1s, 0s. Okay, so this s, here's the path of that s. It stayed the same. Then it became this guy. Okay, and then it became this guy, and ultimately it became 1, 0. Okay. So this S and this S ultimately transitioned to different things. This S transitioned to nothing, and this S transitioned to 1, 0. So unlike a mathematical variable, which is just standing for something that we don't know, it's an unknown, but it's the same unknown in both spots, a context-free grammar variable is not standing for the same string in both of these spots. Okay? And that's a sort of an important observation. So it's better to think of this context-free variable S as representing a string from the language which starts at S. So here, this is a string from the language which starts at S. And this is another string from that same language, but they don't need to be the same string. Okay? So that's an important observation. I mean, you may have noticed it from this derivation, but I just wanted to make it absolutely clear that the fact that this is S doesn't mean that you have to replace both of these with the same thing. Okay? You replace this guy and this guy in totally independent ways. Okay? You can almost think that this guy follows its own derivation, this guy follows its own derivation. Okay? You can get those two results and plug them in here. Okay? So some sort of details about what's going on in a context-free grammar. Okay, let's do some examples from real life.